Hello friends, welcome to the another segment of Polymers in Electronics. Here we are going to discuss the epoxies under the edges of polymer process engineering. Now we have already discussed about the polyurethanes in the previous lecture, in which we discussed about the introductory part of the polyurethane, then we discussed about the various modes of the formation of these polyurethane, then what should be the catalyst selection mechanism in the processing of polyurethane, then we classify them, and then we discussed a lot of testing methods based on the ASTM standards, American Society for Testing Materials. Here we are going to discuss about the epoxies. The epoxies are playing a very vital role in the polymer synthesis, especially in the electronics application. Then we cannot overlook the importance of epoxies, and that is why this particular segment is divided into three broad segments. One is the introduction, then we will discuss about various classification streams of epoxies, and then we will discuss that how we can synthesize those epoxies. Now the epoxies, they are the class of thermosetting polymers, that is the cross-linked polymers, that contains the epoxide functional group, which is represented as CH2CHO, and they are formed by the reaction between the epoxide precursor and a hardener or a curing agent, which cross-links the polymer and imparts its unique properties. And these epoxies are widely used in various industries like aerospace, automotive, construction, electronics, and due to their exceptional mechanical properties or the chemical resistance and adhesive properties, they are very much popular. Now, there are a broad spectrum of classification scheme of epoxy coating, because epoxies are very much useful in the coating application. So, first classification is unesterified solution coating. Now, the two component epoxy, their types are used with the curing agent like amine, polyamide, acid anhydride, and other active hydrogen containing compound. Now, the solid high molecular weight resins, this can be dissolved in organic solvent to prepare the solution coating. Now, these solutions can be modified with other resins like urea formaldehyde, phenol formaldehyde, or melamine formaldehyde. These are the common polymers being used in variety of applications. One is the electrical switches and all those things. Now, solution coating, this can be cured at a room temperature or elevated temperature depending on the reactivity and amount of curing agent used. Now, heat curing, this requires removal of solvent by allowing an air drying period or a step-by-step cure. Sometimes entrapment of volatile or solvent is a serious problem in the solution coating. Now, incorporating the certain pigments, because pigments and fillers, these are useful and these are very useful to impart the desired properties in the coating, and therefore, the incorporation of the pigment and filler cannot be overlooked. So, incorporating certain pigments and filler, this can help in releasing these solvent during the cure cycle. Another form is the esterified solution coating. Now, esterified solution coating are those in which the free hydroxyl groups along with the polymer chain, they have been pre-reacted with organic acids. This group of unsaturated fatty acid esters may be grafted onto the epoxy backbone chain as per the several generalized equations. One of the examples are epoxy esterified with soybean oil, linseed oil, castor oil, or other unsaturated fatty acids. Then metal naphthaletes, they are dried, used as an esterified epoxy formulation like in alkyd coating. Now, both air drying and baking type coating, these can be formulated with these kind of dryers. Baking type enamels, this can cure at the room temperature, and sometimes at higher temperature, that is ranging from 60 to 180 degrees Celsius in 20 to 60 minutes. So, if you lower the temperature, then obviously the time domain would be on the higher side. The addition of unsaturated chains in the resin results in more classical air oxidation curing mechanism and reducing the cost and achieving intermediate properties between non-esterified and alkyd esters. Then 100% solid coating. The 100% solid coating are two component non-ester type formulated without solvents or volatile ingredients, and these coatings are called 100% solid because they do not contain any kind of solvent, so they are perfectly solids. And the resin used in these coating has a low enough viscosity to serve as both a vehicle and a reactive component. Now let us talk about the epoxy synthesis. The general steps usually involved in the synthesis of epoxies are selection of epoxide precursor. This is very important. Now the epoxies can be synthesized from a wide range of epoxide precursor like glycidyl ethers, cycloaliphatic epoxides, and epoxide soybean oil, and among others. Now the selection of the precursor depends on the desired properties of the final product. Now here you see that the various structure and the physical parameter of dye and polyol used for the synthesis of epoxide. Like here different type of names like bisphenol B, bisphenol A, bisphenol C, bisphenol E, all these are enlisted, and here you see the different structures of these components. Apart from this, the melting point, you can see that the melting point varies from 123 to say 217 to the higher, and the boiling point right from 220, 412 to 224, and the density. But the crucial part is their application. So the application like high performance general purpose epoxy, you can use the bisphenol A. Then high performance waterproof epoxy coating, then you can use the bisphenol B. And if we are looking for the flame retardant high performance epoxy, bisphenol C offers a better candidacy. Then resin injection repair if needed, then bisphenol E. Apart from this, other bisphenols are bisphenol F, bisphenol S, bisphenol A, bisphenol M, and bisphenol AF. Now here you see that they are having the wide range of uses like high performance solvent free epoxy coating to the thermostable and flame retardant epoxies, then electronic enclosures, the flame retardant epoxies, and high solid content coating adhesive laminates and low dielectric material. Now you see by this way there are wide range of their applications. Apart from this, there are certain more advanced epoxies like Novolac. You see the structure, and this is having the high performance thermostable low dielectric epoxy. Apart from this, monoglycerides of vegetable oils, you see that this is the typical structure of vegetable oils, and they are flexible and biodegradable. So if because of the environmental constraints and specific properties, if you are looking for the suitable thing, then they offer the better candidacy. Then if we are looking for the tough and biodegradable epoxies, then fatty amide oils of vegetable oils, they are offering a better candidacy. And if we are looking for the low viscosity flexible epoxy, then there are certain aliphatic diols. Apart from this, the hydrogenated bisphenol, they offers this, see the difference in melting point and difference in the density. They are the weather resistant and the color stable epoxy. Then if we look about the glycerol, they again very common. I mean, if we are looking for the cost size aspect, then glycerol is having a prominent place. They are high performance biocompatible hyperbranched epoxies. Apart from this, some of the more you can say more synthesized epoxies, if we are looking for the hyperbranched epoxies, then they offer the very good thing. Then sorbitol, they are the biodegradable hyperbranched epoxies. So these are the some of the epoxies which we have enlisted, apart from their molecular weight, apart from their density and all the applications. Now let us talk about some of the conventional epoxies in a more detailed manner which we enlisted in the tabular form. One is the bisphenol A resin. The bisphenol A, sometimes referred as a BPA, they are formed by the reaction between the BPA and the cross-linking agent, and typically a phenol formaldehyde resin which imparts its unique properties. There are several key properties associated with this BPA resin or bisphenol A resin. They are high, stiff and toughness. resistance to a wide range of chemicals. This may include the acid, base, solvent, fuels, etc. They are having the excellent adhesion properties, having the low shrinkage once they cure, and good thermal stability. Their uses are production of the composites, coating, adhesive, and electrical insulation, and they are also used in the production of epoxy resins, which are similar in structure and properties to BPA resin, but they are formulated with a different curing agents. But there are certain environmental concerns are associated. This has been controversial compound due to its potential health effect on human and the environment, and it has been shown to have the endocrine disrupting effects, and it's been linked to several health issues such as obesity, diabetes, and cancer. So, as a result, there has been growing interest in developing the alternative resin that do not contain BPA. The Novolec resin. Novolec resins, they are the type of thermosetting polymer that are widely used in various industries like coating, adhesive, and composites. Now, these Novolec resins, they are formed by the reaction between the phenol and formaldehyde, and which forms a highly cross-linked polymer with a high degree of aromaticity. Now, the Novolec resin, they have the several key properties like high thermal stability. Now, these Novolec resins, they have excellent thermal stability, and they can withstand with high temperature without degrading or melting. Now, this makes them ideal for use in high temperature application like coating, adhesive for the aircraft and aerospace, and also this has been used for when there is a wide range of delta T, like if we use for in the aerospace, they may have from minus 38 degrees Celsius to say 47 degrees Celsius. So, a lot of thermal thrust are involved, that is why they are being used in that particular application. Then the flame retardancy. It has a good flame retardant properties which make them suitable for use in applications where fire safety is in question. Then the electrical properties, the high dielectric strength and a low dielectric constant. This makes them ideal for the use in electrical insulation application. Now, let us talk about the other epoxy types. The epoxy resins, they may also be prepared by reacting unsaturated compounds like compound containing double, triple bonds, and they are having the oxidizing agents such as peroxide or peracids. Now, both linear and cyclic unsaturated compound may be prepared in this type of aspect, and peracetic acid method is being used commercially, and the epoxy resin prepared in this way have become known in the trade as peracetic acid resins. Epoxidized polyolefin resin, they have the distinct molecular structure compared to the bisphenol A series. Now, while both containing epoxy ring, the position of the ring differs between these two. In epoxidized polyolefins, the epoxy resins, they are present both along the chain and at the chain end, whereas in the bisphenol A series, the epoxy ring, they are exclusively located at the end of the chain. Now, epoxy polyolefin resin, these can be cured with the common hardeners and catalysts used for bisphenol resin as well as the free radical initiators due to many double bond presents. Dicumyl peroxide and other peroxide catalysts, they can also be used to cure these resins. Now, peracetic acid resins, they have the lower densities compared to bisphenol epoxy resin and making them suitable for some airborne electronic application. Uncured peracetic acid resins, they are about 20% lighter in weight. So, in one aspect they are very much beneficial, and these resins have better high temperature performance and resulting in a similar weight loss. They have comparable the electrical properties, chemical properties, solvent resistance to the bisphenol resin. Now, sometimes the addition of hardener is very vital. So the epoxide precursor is mixed with the hardener or curing agent which reacts with the epoxide functional group to form a three-dimensional network of polymer chain, and this makes them harden and harden. The polymerization process typically involves in different steps. First step is the mixing. The curing agent is typically mixed with the polymer resin in the specified ratio to form a homogeneous mixture. So this is again important thing. And then initiation, because we are performing the polymerization process, so initiation must be there. So the curing agent initiates the polymerization process by reacting with the functional group on the polymer resin which is already present, and typically epoxide or amine group. Now this reaction leads to the formation of reactive species such as free radicals or ion, and which can react with other molecules to form a new bonds, or this can be act as a source material for the propagation step. Next step is the propagation. The reactive species continue to react with the other molecules to form the longer chain which propagate throughout the mixture. The only thing is required, they must have either free radical or ion in situ. So this leads to the formation of a three-dimensional network structure. Then cross-linking. The polymer chains continue to react and cross-linking with each other, forming a stable and a rigid network structure. Now this process is often accompanied by the release of heat and other byproducts. The specific curing agent used depends on the type of the thermosetting polymer and the desired properties of the final product. Common type of curing agent includes amine, anhydrides, acids, and peroxide. The choice of curing agent also affects the curing temperature and time required to achieve the desired degree of cross-linking and properties. Now here we have enlisted some of the structure and application areas of hardener used in epoxy coating. Like if basic thing in our all application is the application arena. Now if we require the things at fast room temperature curing, then we are having this one, then triethylene terramine, then the fast room temperature curing, then thermostable epoxies if we are looking for, then the suitable way is hexamethylene diamine. Then if we the application requires the tougher epoxies, then polyoxypropylene diamine, this one. And if we require the room temperature curing, then N-amino no ethyl piperazine. So by this way, there are so many hardeners they are used for this epoxy curing, like diaminopenyl sulfone, then methylene. Like if we require the good physical and dielectric properties. Apart from this, the trimetallic anhydride, if the thermostable high performance epoxy thermoset applications are needed. Similarly, if we are looking for the low temperature curing, which may be tough and biocompatible epoxy thermosets, then the vegetable oil based polyamide, this can be used. And if we are looking for the thermostable epoxy thermosets, then nadic methyl anhydride can be used, which is having the structure like this. And if the application involves the biocompatible and biodegradable epoxy thermosets, then polyphenols like such as tannic acid, this can be used. Now let us talk about the curing agent and polymerization process. First, let us take up the catalytic polymerization. The catalytic polymerization can be initiated by the Lewis acid and Lewis base compound like boron trichloride, boron trifluoride, aluminum chloride, and tertiary amines. Lewis acids, they act as an electron acceptor, while Lewis bases, they act as electron donors. Now tertiary amines, they are commonly used as catalysts for curing low molecular weight glycidyl ether resin, and this required the slightly elevated temperature, high molecular weight resin with more hydroxyl groups. This can be cured at a room temperature. Now tertiary amine catalysts, they are used in the quantities of say 5 to 15 parts per 100 resin. while Lewis acid or amine complexes, they are used in amount of say 2 to 4 parts per 100 resin. Now handling free Lewis acid and bases can be challenging due to their corrosive, irritating or toxic nature as well as their reactivity in a short pot lives. Highly reactive catalysts like boron trifluoride, they are typically sold and used as a latent complexes or modified to reduce vapor pressure, toxicities and extend pot lives. Now the boron trifluoride, this can be employed as an amine complex such as aniline, boron trifluoride or trimethylene boron trifluoride, which gradually dissociate at room temperature or more rapidly with application of heat or other form of energy. Now, catalytic curing agent, although effective, have not been widely used in coating formulation compared to the polyamide and other additive hardeners. Now, let us talk about the polymerization with the amine hardeners. Now, amine compounds, they are widely used as a curing agent for epoxy coating. They offer fast curing at room temperature or shorter curing time at higher temperatures. Now, polyamines, they are commonly used in concentration of 4 to 20 parts per 100 resin. Now, epoxy coating cured with amine compound exhibits excellent chemical and solvent resistancy, electrical properties, and they possess the thermal and vacuum stability. The post-curing or elevated temperature curing further enhances these properties, and these are the various generic structure type of amine compound used as a curing agent for epoxy coating. Now, commercially available amine curing agents, they are often modified to reduce vapor pressure, decrease skin irritation and control pot life. These modified amine, this can be used as eutectic mixture adduct with the lower molecular weight epoxy compound or complexes with boron trifluoride. Now, if we talk about the amine hardeners, as we are discussing, the primary and secondary aliphatic and aromatic amines, they are reactive with the epoxy resin at a concentration of 10 to 15 pHr. Ethylene diamine is an example of an amine that participates in the epoxy cure mechanism, resulting in high molecular weight thermosetting epoxy coating. Modified amine compound, this help in reduce the skin irritation, noxious odor and corrosiveness, and they extend the pot life of epoxy formulation. Polymerization with acid and anhydride hardeners. Organic dicarboxylic acid and anhydrides, they are commonly used as epoxy curing agents in solution coating, and they open up the epoxy ring and become incorporated into the structure as ester. The example of dicarboxylic acid includes oxalic acid, HCOH, COOH, which is used in various coating formulations. The formulations using dicarboxylic acid have a pot life of several days and can be cured at temperatures ranging from 125 to 175 degrees Celsius for 1 hour or even longer. Other dicarboxylic acid in the series like HOCCH or COH with N ranging from say 1 to 8. They are less popular for solution coating due to their insolubility, difficulty in mixing with the resin and tendency to foam the resin. So, all these are contributing effect. Now, anhydrides derived from the carboxylic acid, they are more commonly used and offer advantages over amine cured system. An anhydride cured system exhibit better thermal resistance and higher distortion temperature 40 to 60 degrees Celsius and improved electrical properties. Now, low dielectric constants such as 2.8 to 3, this can be achieved with anhydride curing agent. And anhydride curing agent, they are typically used in the concentration of say 30 to 140 parts per 100 of resin, and they often require the accelerator or catalyst to promote faster reactions with epoxies and especially with the liquid type. The addition of a smaller amount of a tertiary amine catalyst, say in the 1 to 5 pHr, that is parts per 100, this can result in the stable epoxy composition with low viscosity at room temperature and rapid curing at 120 degrees Celsius. Now let us talk about the polymerization with polyamide resins. Now the polyamide, they are resinous polymer used as epoxy curing agent, and they are based on vegetable oils and should not be confused with nylon type of polyamides. And epoxy curing polyamides are condensation polymers of dimerized or trimerized vegetable oil or unsaturated fatty acids with polyamines. So the amino group in the polyamide structure with both primary and secondary, they are epoxy reactive and not the amide groups. The hydrogen of the amide group is non-reactive due to its low acidity or reactivity. A typical structure of polyamide resin is based on dimerized linoleic acid or diethylamine data. Now, example is dimer acid based polyamide resin. They derived from the vegetable oil and polyamines. Now, trimer acid based polyamide resin, they derived from unsaturated fatty acids and polyamines. The polyamides based on the soybean oil and polyamines, they are very much popular, and they are also derived from the castor oil and polyamines, and the specific structure and the properties of polyamide resin can vary depending upon the choice of vegetable oil, polyamine and reaction conditions. So, all the reaction parameters plays a very vital role irrespective of their soybean oil or castor oil or any kind of a vegetable oil which you are using. The presence of a free secondary amine group here like this enables the cross-linking of epoxy resin change. The reactive sites of cross-linking, they are located on the secondary amine groups, and the R groups, that can be either another linoleic dimer portion or a hydrogen atom. Now let us talk about the latent curing agent. Now some compound similar in structure to the polyamides but unreactive with epoxies at room temperature may decompose into active amines at elevated temperature. A classical example is diamine or dice, a solid latent type of curing agent which represents a special type of an amidine. Now, when we are talking about the synthesis, let us talk about the catalysts. The reaction between the epoxide precursor and the hardener is catalyzed by a catalyst like Lewis acid, usually which accelerates the reaction rate and improves the quality of the final product. Now, catalyst used in the preparation of glycidal ether epoxies to remove HCl during the polycondensation. So, there are various things being used like sodium hydroxide, potassium hydroxide, calcium hydroxide, lithium hydroxide, sodium carbonate, calcium carbonate, potassium carbonate, sodium bicarbonate, potassium bicarbonate and calcium bicarbonate. So, these can be used for the same. Lithium bicarbonate is one of the popular and this is most commonly used catalyst. The coordination compound based catalyst usually mentioned cobalt or nickel with the acetylene ligand. Now tertiary amines, that phosphines and quaternary ammonium salts used with the reaction media like tetrahydrofuran, acetone, dimethyl sulfoxide and dimethyl formamide. Tertiary amines and quaternary ammonium salt preferred as catalyst in polyaddition reaction, and a stoichiometric amount of catalyst they are required for the reaction to progress, and catalyst for the non-glycidal epoxies, this can be used as the hypohalous acid, sulfuric acid, hydrochloric acid, nitric acid, phosphoric acid and transition metal based catalyst. Now, catalysts that are used in pre-carboxylic acid based epoxidation reaction of vegetable oil or olefinic double bonds. Now, enzyme can also serve as a catalyst in these reactions. Let us talk about the post-curing. After the initial reaction is complete, the epoxies may undergo a post-curing process to improve its mechanical properties, thermal stabilities, and chemical resistance. Now, this is achieved by subjecting to epoxies at elevated temperature for a certain period of time. So, dear friends, in this particular segment, we discuss the all aspects of epoxies, which are again the integral part of electronics application, especially in the polymers. We discussed the classification, we discussed different mechanism, we discussed different processes like initiation to propagation and all those things. And for your convenience, we have been listed a couple of references which you can utilize if required. Thank you very much.